Okay, hello everyone. What did we learn last time? Yesterday.
Change of basis.
What did that mean? The
Instead
question
of
is.
using the basis of like
Yeah.
just 1, 0, 0, 1, using bases of different values and seeing how to go between the different kinds of bases.
Right. So last time we start from the standard basis. Is that okay? So we start from the standard basis, right? And then we try to see how we can express this black vector, right? And then we try to, and that was this, right? If we try to express 1, 1, using two standard vectors, it was like this. What if we try to use different bases? For example, like this. Okay? And then the answer we got is this. Let me ask one thing. Is it unique?
Yeah. Yes.
So that is another true-false question right there. True. So if I ask, hey, is it true or false? There's many
False.
Oh. Okay. So this chapter is about eigenvalue and eigenvectors. During the first and second week, when I asked you to present yourself, like when I asked you to introduce yourself, you talked about your major, and then you talked about some applications in your major, right? And then a lot of you guys talked about eigenvalue and eigenvectors. Now we finally learn. Before I even talk about what eigenvector or eigenvalue is, I want to ask you to calculate A times U. Give me the answer. -5, -1? Is it what you said?
Yeah.
Okay, good. What about, is it right?
Yes. Yeah.
Going down. A times B. What is A times B? 2. Sure? So what is A doing? So I give you a random vector U or V. I want you to multiply A times U. What does it do?
Essentially, it's acting like a scalar
Acting
on each of those u or v.
Oh, good. So this is my starting point. I mean starting vector U, and I transform that vector U using matrix A, right? And then this is the result. So again here, I give you some random vector that happens to be V, and I multiply that, multiply V by A, and this is the result. So essentially, I start with some 2 arrows, and I transform that, and that will be this. So I start with U, I use matrix A to transform this. This is what I get. Also V here. This is AB. This is the result that I get. Do you see any characteristics of this transformation?
It's bigger.
Eh?
It gets bigger.
Gets bigger.
It increases the magnitude of U and V.
Okay, so you have U, right? You rotate this direction, right? And then you scale and you stretch this, right? What about V? Do you rotate?
No.
You don't rotate, you rather stretch, right? So can I express this scale of V. What is it? Any relationship between 4, 2, and 2?
Yeah, it's double.
Yes, double. 2 times V. Right? This is eigenvector. So you have the transformation matrix A. You transform some random vector using that A, the matrix A. If you get a scaled version of the original vector, that is the eigenvector. The U is not eigenvector because you already rotate this. It's not scaling. You have the rotation involved in it. But here you only stretch. Right? So if I read this, AV is just 2V. So A only stretches or dilates V. However, U vector U, you rotate also stretch.
So, is that more dependent on A or on B?
Both. So depending on what A is, you'll have different vectors, eigenvectors, right? And then once you have some random matrix A, and you may have it totally depends on what your choice is for A. Let's say, you guys remember from the chapter, I think it's chapter 2. We had picture, original picture, and then we try to rotate this. If I have to rotate, I think this is chapter 2. That's a really good question. Very good. One second, guys. It's coming up. I need to do that. Oh, here we go. So, for example here, if I draw any vector, any arrow, if I'm rotating it, the transfer matrix itself is rotating matrix, then you will never have an eigenvector. Right? However, like, oh here. Let's say this. What is this? What is this transformation matrix? You have an image. You rotate. You reflect this image based on this one, right?
So it's reversing the image?
Yes, yes. But if I pick a vector, pick a arrow along this line, it's not going to do anything. So any vector along this line is going to be an eigenvector. Here too. So let's say I have the original image, like image of sheep. Yeah, what is it right here? Sheep. No, sheep. Okay. So these two, there are two different transformations. Let's talk about this first. If I pick a vector along this line, it's not going to be anything. So along this line, it's going to be eigenvector. Also here. Okay? Let's back to the. I mean, to answer your question, yes, depending on the choice of matrix A. So depending on matrix A, you may have eigenvector or you may not. Okay, so this is what we just talked. I pick a vector, transform this using A, and it ends up being 2 times that. Yes.
Going back to the problem, first one is checked. So every vector spanned by V is also an eigenvector.
Great job. Actually, that's what I'm going to talk about. Always going on ahead. Okay, so yeah, we'll talk about it. So what you said is, what is it? You're gonna have a space that is spanned by a vector, right? That is called eigenspace. Okay, so let's read. Ronald, can you read this?
An eigenvector of an n times n matrix A is a non-zero vector S such that A times X equals how you call that?
Lambda.
Lambda times X for some scalar lambda. A scalar lambda is called an eigenvalue of A. There is a non-trivial solution of X. A times X equals lambda times X. Such an X is called an eigenvector corresponding to lambda.
Okay, so what was the lambda in the previous example? 2, right? So depending on the choice of A, you may have different value for the lambda, also different eigenvector. Okay, so there's a link between eigenvalue and eigenvector. So let's talk about it. If I ask you, I give you 2 vectors. I give 2 U and U vectors. I also give you a transform matrix A. Now I ask you, hey, are these eigenvectors? What would be the proper way to verify this? You just did it.
Find a U and a B and then see if their scales of U and B.
Great, yes. So let's try it. Tell me what is AU? Calculator? 6 minus 30. And what is it? Oh, trust you. And 6 times 5 plus minus. What is it? Okay, good. Okay. Is U eigenvector?
Yes.
How?
-4. Lambda equals -4.
Oh, great. So like this. So this is basically, if I keep writing this, minus 4 times U, right? U. A times U can be expressed by minus 4 times U, right? Okay, so let's say matrix A, this, what is size of A? 2 by 2, right? Let's say you, in the future you're dealing with some like gigantic data and you're trying to do machine learning, you're trying to find the eigenvector. And let's say you found the eigenvector and eigenvalue. Okay? Now you have, in front of you there's a really gigantic matrix A. You know eigenvector and eigenvalue. And I want to multiply that eigenvector by this matrix A. Should I do that? Or instead, should I just multiply that vector by a scalar, which is lambda? Yeah, find the scalar and multiply that. Let's count how many operations we need for this. Multiplication 1, 2, addition. So 3 operations, right? For this entry. How about this? 1, 2, and plus 3. So total 6 operations. Right? So this one. -4 times the vector, 1, 2. So if you have really gigantic matrix, then it is a lot more efficient to just use eigenvector and eigenvalue. Okay? This is one way, this is one of the reasons you try to learn eigenvector and eigenvalue. In many cases, you use eigenvector or eigenvalue to reduce the computational cost. And you encounter it if you take the machine learning class. Okay, what about V? What is AV? Okay, you guys are STEM major, you can do this math in your head.
-9, 11.
-9, 11. Okay. Is this eigen?
No.
There's no way you can skin this to get this right. Okay, so oh yeah, the right answer right here. So if I try to answer this question using tricky math terms, U is eigenvector corresponding to an eigenvalue -4, but V is not an eigenvector because AV is not a multiple of V, meaning scale of V, right? Okay, so here we're still talking about this example. And we got eigenvalue -4, eigenvector, this. And the next question says, okay, what if you have another eigenvalue, which is 7? Verify this. And find me the corresponding eigenvector. You already know how to solve this, right? Because verb reduce and finding solution is gonna do this job. Okay, the setup is okay. What is the definition? Back to the basic. You have transformation in matrix A. You already have it from example 2, right? You already have A. You know what A is, and you already know what lambda is already. Your job is finding X. Okay? How do you do this, guys? You almost, if I talk a little more, you realize. Okay, let's use this. A. Let's copy and paste this. The problem says, okay, you're going to have another lambda that is 7. And by the definition of eigenvalue and eigenvector, you have like this, right? X is not a scalar. X is not a number or a scalar. It is a vector. Size what? It's a vector.
2 by 1.
What?
2 by 1.
Yeah, 2 by 1, yes. Because we have 2 by 2 for A. I want to find X. Isn't it what we did in the example?
Multiply each side by the inverse of A.
Yeah, that's one way too. Yes. My hint is null space. What did we do to find null space? What is null space?
It's creating the matrix and solving for 0.
Yes. So the null space is you got a sum matrix A, and whatever the vector that makes 0, whatever the vector that makes this thing 0, is gonna be null space. So it's gonna be vector in the null space. So this, we learned it last week. I'm trying to use the same technique. So for row reduction, we always have augmented matrix, right? Matrix A, long line, and then constant vector, right? So I'm trying to have that kind of format for this one too. What can I do?
So you're just solving for, instead of 0 for 7?
Yeah, good. I'll do the same thing. So, yeah, good try. So AX, what if I do this? And factor X out. And this is a really typical technique to solve or find the eigenvalue or eigenvalue. Okay. Can I factor it out? How?
Pull out the x. We have x times a minus 7.
Like this?
Hopefully.
If you do this, you get 0 for your example.
So not that.
Okay, why is not true? That's what, huh? Okay, because if we factor out x, that's good. But what we have is matrix A that is size 2 by 2 minus a scalar, just a number. Can you do this?
No.
No. Then how can I transform this? How can I make this thing? Okay, we need another letter that makes this thing valid from here to here.
Maybe not, but I was gonna say you make 7 a vector, like make it 7 and 7, but.
Okay, whoever gives me answer extra 10 minutes.
If we know AX equals, if we can set it to the null space, we can say AX equals 0, right? Is that?
So what I'm saying is, how can we factor x out from here to here? I mean, it's not valid. I'm trying to. How to factor out x? Yes.
You need to factor out the 7. And
Yeah.
then
Seven?
like divide the 7 from the.
What's that?
Yeah. It'll be like a scalar on
Okay, I'll listen to Lucy's.
Can we make 7 like B or something?
B?
Like define it as like a letter vector instead of a number vector?
No. We don't need to be that complicated.
Do we use X inverse?
Okay, so to find the inverse, okay, let's talk about the definition of inverse matrix. To be able to have inverse matrix, the shape of matrix you should have is square matrix. Meaning you have to have the same number of rows and same number of columns. X, size of X is 2 by 1. That's what you cannot. Really? I'll wait 1 over 2
Put the identity matrix in.
Okay. I forgot your name. Chris.
You could just make it Christopher.
Christopher.
So
Because there's
differentiate
two,
them.
yeah.
I'll just stick with Chris.
Okay. So what's your last name?
Joe, so just
Joe. I'll find out.
yeah.
So, okay, great job. So, okay. This thing is 7 times I times x. Okay? 7i. What is 7i? You have just 7, 7, 0, 0. So the identity matrix is you have you have ones on the diagonal line, right? Then if we multiply that identity matrix by some scalar, then you just write the scalar. In this case, we have 7. Right? And this will essentially do the job. Same as multiplying the scalar. So you have x1, x2, a vector. I multiply this by a scalar, 7. And that is equal to, you multiply x by the identity matrix, scaled by 7. Okay? Makes sense? Okay, so So essentially I'm going to do is a minus 7i, that is multiplied by x.
So we can subtract matrices
Subtract matrices?
from each other?
Yes, because they have the same size. The A is 2 by 2, I is, I'm setting I 2. The size of I is 2. Okay, so what is I? Sorry, what is A? This. So what is A minus 7i? Yes.
Minus 6, minus 1, minus 2.
Minus, oh, okay.
Minus
Okay.
five.
So minus 6 and what next?
Minus 1.
No, we
Minus 6, 6, 5, negative 5.
yes. Okay, so David, so the
Oh, right.
yeah,
Yeah.
realize, okay, good. So this times x equals to 0. Okay. Now what is this? Can we find this x? How do we find x? We've done it so many times.
Matrix.
Yes. How? Copy paste this vertical line 0, 0. Try it. Tell me the answer. Tell me x. Minus 6, 6, 5, negative 5, 0, 0. Augment this, give me the solution. Give me a solution.
One negative 1, 0, 0, 0, 0.
Oh, good. Well, I missed you. Yeah, good. Come here more. Okay, so what does that mean? Do you have free variable? X1 is negative and x2, and then x2 is 1. Yeah, free. So meaning you have so many choices for x1, x2. Right? Okay, so how can I write? Back to the question. Let's answer this. Okay. How can I show this? You already got the solution. I mean, as I always tell you, once you have augmented matrix, you already know how to go read this, and you can write solution. And then what? You have to interpret this. Okay? Now, for the exam 2, it's quite important for you to understand how to interpret the answer. But for exam 1, you just don't think just go reduce and get the answer. That was enough for the exam. Yes.
So does that mean that the eigenvalue is 7 whenever x1 equals x2?
That means, okay, visually speaking, let's write it. I'll draw it. So, whenever x1, x2 are equal, meaning I'm gonna have, so if I span that vector, do I have something like this? Yes. So you pick a vector from this line. So 1, 1, or 2, 2, or 3, 2, doesn't matter. That will be eigenvector. Okay? Okay, so if I read the solution. So basically the same thing we just did. I just use 7i and you go reduce, and this is the answer, and then you can summarize the answer. Okay, you pick any value for x2 because x2 is free, and then that is you scale vector 1, 1 using that your choice of x2. Right? then the corresponding eigenvalue will be 7. Okay?
Why 1, 1? Is it just a random or?
Oh, wait, 1, 1. 1, 1 is just scalar. So you can just say, this is standard matrix.
No, I'm saying,
Yeah.
why vector 1, 1? Can it be any vector? In like that line that you were saying?
Yeah, so let's try this. Okay, so
And one would be like the base vector, but that's, yeah.
yes, Dylan, you're correct. Actually, this next chapter we're gonna talk about. So this is going to be the eigenbasis. We're gonna learn next chapter. So you have some base vector, right? And then you scale that, and then it's essentially the span the space. You pick any vector from that span, then that'll be always eigenvector, and then the corresponding eigenvalue will be set. I
So
will-
given some matrix A, if we were solving for some eigenvalue that we wanted to solve, that would produce a unique scalable eigenvector we could find potentially.
Yes. Good. Always Dylan impress me. He always summarize what I'm talking about. Always impress me. Okay, so Dylan, can you read this? Quite long.
Warning, although row reduction was used in example 3 to find eigenvectors, it cannot be used to find eigenvalues. An echelon form of a matrix A usually does not display the eigenvalues of A. The equivalence of equations 1 and 2 obviously holds for any lambda in place of lambda equals 7. Thus, lambda is an eigenvalue of an n by n matrix A if and only if the equation A minus lambda times the identity times x equals 0 has a non-trivial solution. The set of all solutions of 3 is just the null space of the matrix A minus lambda I, so this set is a subspace of Rn and is called the eigenspace of A corresponding to lambda. The eigenspace consists of the 0 vector and all the eigenvectors corresponding to lambda.
Okay, Chris, you want to talk about the eigenspace? Good job. So, okay, so what is my non-trivial solution? So let's say I do this. So let's say we have different choice of A, and I did it, and then after some row reduction, let's say I'm assuming a different situation. Let's say I have 1, 1, 0, 0, 1, 0, 0, 1, 0, 0. What is the solution? Yeah, 0, 0. That is
Trivial.
trivial. That is, you don't have eigenvector. Okay? I mean, in this case, that's what it's saying. In this case, the 7 is not eigenvalue, sir. So 7 is not eigenvalue. Okay? In this case. Because the reason we start with this is I want to verify if 7 is a eigenvalue, and that's why we start with this. Okay? And at the end of the solution we got is essentially we got 0, 0, that's why it's not. But anyway. So let's visually understand. Valerie, can you read this, please? Can you see?
Example 3 shows that for matrix A in example 2, the eigenspace corresponding to lambda equals 7 consists of all multiples of 1, 1, which is the line through 1 to 1. And we already, from example 2, you can check that the eigenspace corresponding to lambda equals -4 is the line through 6 minus 5. These eigenspaces are shown in figure 2 along with eigenvectors 1, 1, and 3. 3 over 2 and -5/4, and the geometric action of the transformation x to ax on each eigenspace.
Okay, so let's understand this. So these two lines are eigenspace of this matrix, the matrix we just talked about. Okay? So far we're talking about this matrix, okay, this transformation matrix. And then at the beginning, what was with that transformation matrix, if you pick a vector like this, and it's gonna rotate. However, if you pick a vector along this line, from this space, you never rotate. You're just gonna stretch by 7 if you pick a vector from here. If you pick a vector from here, you're not gonna stretch, you're not gonna rotate, but you're gonna flip because you have minus, and then you're gonna stretch by 4. Okay? Make sense? So let's say I start with 1, 1. And what is the A matrix? Matrix A is I want to multiply so if I pick a vector from along the line and I multiply that, I need visual. Again, so I pick a vector 1, 1. You multiply that by A, and this end up being just 7, 7. Which is 7 times 1. Okay. Same here, you pick a vector, let's say this is negative 2. Yeah, this one. Let's say I pick a vector like this. It's going to be 1.5. I don't know the exact value. Anyway, so you pick a vector, you multiply this vector by A, and what you're gonna get is this vector. This is the result you get for A times this blue vector. Okay? Okay, how can we start with this? Yes. Yes.
I have a different question. Is eigenspace just the combination of the eigenvalue and the eigenvector?
Yes. Good. So, let's say you have some eigenspace, and you gotta have there must be eigenvalue, also eigenvector along this. So let's say you're talking about this eigenspace. Okay? You pick any vector from eigenspace, and that is going to be eigenvector, right? And then you multiply that eigenvector by A.
Eigenvalue.
Yes.
But an eigenvalue is also any scalar, right?
Yes, any scalar. That's why it's so handy to use this, because instead of multiplying the gigantic matrix, I'm just going to use a scalar.
So an eigenvalue is any point along that vector? Is that?
Any vector, any arrow from this space.
Okay.
Makes sense? Sure. Okay, so I want to find a basis. Let's say I give a matrix A, in this case we have 3 by 3, bigger, and I tell you, okay, eigenvalue is 2. Lambda is 2. I want you to find eigen space essentially. Because if you find the space, then you can automatically find the basis. How can you do this, guys?
We subtract 2i3 from matrix A and then set it equal and not when matrix is
Oh,
0.
okay, perfect. Let's do it. So let's try that. So using so basically the only definition we so far we learned is just this. Just this. So I'm trying to utilize this definition. So let's do one thing. So I'm gonna have a times x, that should be equal to eigenvalue times x. And I'm gonna use the same technique, right, like this. And I can factor out x. Right? Right? Then what?
Subtract.
Yes, that's a minus 2i, what is it? A minus 2i, what is it?
To a negative 1, 6, 3 times.
Is it right? Is it right? Everything's same. I mean, the entries not on the diagonal line are gonna stay same. And the only diagonal lines are gonna be subtract how much? By 2, right? Okay. So this is the matrix segment. And then I want to find the x that makes this thing true. What do we do?
So, for 0.
I mean, yes. Then, how do you do it? How do you find the solution? Augmented matrix. Right? Makes sense? Okay, so essentially you got this, and you write augmented matrix, meaning you're going to have all zeros for the last column, right? Reduce it, let's say the result you get is this. I mean, once you see this, it's quite easy. It's just linearly dependent. How many?
Two free variables.
It's quick. Top up. Let's just forget about this. If I ask, hey, rank of this, what is it? Just forget about everything, just
1.
yes, why? Why? After we reduce, the pivot you got is just only 1 here. And everything else 0. Then what is the null space? I mean, the number of null space?
2.
2, yes. Anyway, back to question. So you got this. And then how do we write the solution?
X1 equals 0.5 x2 minus 3x3.
Yes. Yes. I think. Right. So what about x2?
X2 and x3 are free.
Okay, so how can I write the solution? Let's say I want to rewrite. I think this is x2, x3. Okay. Again, I told you guys.
Make it 3x1 matrix
Yes, 3x1 matrix.
with the first entry being 0.5 x2 minus x3, the second entry being x2, and the third entry being x3.
Can you say again?
3x1 matrix, first entry 0.5 x2 minus 3x3, second entry x2, and the third one is x3.
Can you write it? Sometimes I'm dead.
So I did like that.
Oh, perfect. Actually, this. Okay, so what does it say? So how many trivials do you have? Okay. So back to the question. So, as I told you, if I ask you to roll reduce, you'll do it, you'll nail it. But once you get the answer, what does this say?
That's the span of the eigenspace.
Yeah.
Yes. Then what is the basis? Find the basis. What is basis, guys? Yes. So you got a space, right? So what is basis of this space? Guys, what is it? What is it, guys? No, I'm asking. So what is basis? What basis? So what Chris expresses, this is eigenspace. I understand. Whatever you pick for x2, x3, we're gonna have some vector, and that vector is gonna lie on that space. It's eigenspace. Okay, got it. Understand. Next question. What is basis from the space? What is definition basis? So this basis is only this two. How do you write this? Base span of those two vectors, right? 5, 1, 0, and negative 3, 0, 1. This is the eigenspace, right? These two are the bases. Right? So, here. The basis is this. I mean, if you scale this by 2, it's still the same. But you can just write basis this 2. Same. Does that make sense? Really? Seems like no one understands it. I mean, as I told you, if I ask you to vote this, you would nail it, but after this, you get the answer, but how do you interpret this? This is another step to master. So, one step forward. Okay. Span of a vector. What is the shape of the space? Let's say, I'm trying to make sure you guys understand. What is the difference between these two?
One is line, one is a plane.
Oh, great job. Why?
Because there are two independent vectors and you need three if it was the whole span of the 3D space.
Yes. So essentially, if you have one independent vector, span of that is going to just align along that vector, right? If you have two independent vectors, right, then span of those two is going to be a plane, right? It's like a slice of cheese. Right? So if you visualize this, something like this. Why do you have three-dimensional space? Because we're playing this game in the 3D. Because we have three entries, right? 1, 2, 3. Right? And then this is the eigenspace that is spanned by two vectors. Right? Those two vectors are this. Okay? And so, what is this? What is this? Explain this. Why this picture is explained like this? 10 extra steps. What is it?
max it can span off the lambda too, like those, the
Max?
Yeah.
You say max, maximum max.
Maximum?
A little bit off, yes.
Scaling was by choosing the first one by two.
Oh, yes, yes, Joseph. I'll give five points, because you tried, but Joseph will get. Joseph, and, one, plus one. Anyway, so, why though, why? So you pick a vector from the eigenspace, right? Right? You transform that vector, let's say I pick this from the eigenspace. Now I want to multiply A by this vector, right? I don't need to do any complicated calculation. I just need to multiply this vector by the scalar, which is eigenvalue. Okay? That's why it says, okay, you pick a vector, it's gonna just stretch by 2. Okay? Make sense? Yes.
What would the eigenspace for lambda equal to 3 be? Would it be like shifted up, down, or would it just be larger on the same, or longer on the same plane?
So what you're saying is that, so if we have a different matrix A, and we happen to have eigenvalue 3, okay, and we happen to have 2 bases for the eigenspace, then it's going to have, we're going to have 2-dimensional eigenspace, right? In this case, plane, right? So in that case, then you pick a vector from the eigenspace, then you're going to multiply that vector by the scalar 3.
Oh,
Yeah.
so instead of like over, it'd just be longer?
Yeah, longer. Yes,
Okay.
yes. So we may not have 3 for the eigenvalue, for this particular matrix A. We may have, so in the case, if we have different matrix A, then we may have the 3 for the eigenvalue. Then yes, you're right. Okay. So here, property. Eigenvalues of a triangle matrix are the entries on each diagonal. This actually I want to force you to know that because it's very useful theory in machine learning. It's very true or false. I actually hate to force you to memorize it, but really I want to emphasize this. There's proof, but okay, so I want to use this theory. Let's say I give you a matrix A. Brian, can you read this?
Which one?
This the purple.
The eigenvalues of a triangular matrix of the entries on its main diagonal.
Okay, so I want to use this theory. I give you a triangular matrix, meaning I'm gonna have a triangular shape entries like it's like along. I can break this matrix into 2 triangles, right? 1 and all zeros. Okay. So I got a triangular matrix. What is eigenvalue? What is eigenvalue?
So 302.
Yeah, that's it. It's 3. It's 3. Why? Because theory says the eigenvalues are going to be the entries on the main diagonal. So here. So what about this? B. Yeah, I'm just testing if you have eyes. 4, 1, 4. So 4, 1. Try this, guys. Anyone who wanna solve this on the board? 5 points. Well, I mean, marking is asking us for, hey, 5 double, 5 double.
just say no?
Yes, Thomas?
No, I have another question.
Always,
Yeah.
always.
I'm trying to understand why are we specifying specific eigenvalues, but I thought there were like unlimited amount of eigenvalues for a matrix. I thought it was just like a scalar.
No. So for a given matrix, the maximum number of eigenvalues you can have is the number of diagonal entries. So if you're talking about a square matrix, then the limit is n. Yes. Yes. So here, fixed. So for this eigenspace, you're bound with this eigenvalue. Also same here. There's no other eigenvalue. I mean, if you have different matrices, yes, you're gonna have other eigenvalues. But let's say you already had matrix A, and then from that you can find the eigenvalue that is maximum 2 if the size is 2 by 2. Yeah, there is a limitation. Okay, solve this for 5 points. No more volunteer? 7 points.
Or you go higher.
It's not like option. 10 points. Okay, come on. You guys are ready for the moment. 10 points. Okay.
Shit, how about for 20? So can you do that one as a triangular matrix?
No, because from the beginning, the previous example we had is from the beginning, the given matrix was a triangle. That's why we can find the eigenvalues immediately. But here, finding eigenvalue is another story. But verifying if 5 is eigenvalue is easy, because all you need to do is, Dylan. All you need to do is ax equals to 5x. Find the solution. If you can find non-trivial solution, then this is true. Yes.
Can 0 be an eigenvalue?
No.
Oh.
Yeah, in the case, yeah. Sorry. Did you ask 0 0 can be eigenvalue? Yes.
Oh, okay.
Yes, in the previous, like this. I thought you were talking about.
So would that
Vector,
just mean that transforming any vector with 0 as an eigenvalue just makes it 0?
Yes. So, yes, correct. Yeah, I'll share the link YouTube video that explains that concept really well. So basically, if you from that eigenspace, you're gonna just crash that everything to 0. I'll share the link. Okay, what he is essentially doing is same thing. So you subtract a, you subtract 5 from a. So 5 0, and then you find the null space. And how to find the null space? Augmenting matrix.
So since I have 3 pivots and they're all linearly independent, that means 5 can't be an eigenvalue.
And because we have only trivial solution, right? The only solution you got is trivial solution. Therefore, this is not eigenvalue. Okay. So thank you very much. So let's say this subtract 5 from diagonal entries. let's say you successfully will reduce. Okay. And once you find out 3 pivots, that means all 0. Right? Therefore, the only solution I have is trivial solution. Therefore, 5 is not eigenvector. Okay. Okay, so last one is a very, 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 very important one. What is this? Let's say x is eigenvector and then lambda is given and that lambda is corresponding eigenvalues for x. Okay? And I happen to want multiply a cubed by x. Let's say A is million by million, a really gigantic matrix. Do I need to do this?
No.
Yes, because this says it's essentially ax is equal to lambda x. Okay, A is trillion by trillion, really gigantic matrix. So let's say you're Netflix machine learning engineer, then you're gonna have billion by billion, right? The users are billions. Right? Then you don't want to calculate this so big. If you know eigenvalue, okay, billion by billion, you multiply that 3 times, it takes forever, unless you have really supercomputer. So this can be equal to this. Okay? Okay guys, time's over.